So this is Discrete Mathematics tutorial 1. I'm just going to try to make it quick because we want to cover a lot of topics. But I'm sure you have done, since you have done your assignments, I'm sure you have the know-how of what you are supposed to do here. So I'll actually ask some questions. Yeah, to make it interesting, I'll ask some questions. Yeah. And I'll look forward to see some response from all of you. Okay, so without wasting much of your time, let's begin our tutorial. So we're going to start with the greatest common divisor, the GCD. So the greatest common divisor, written as GCD of AB, is the greatest common divisor of A and B. So what you are saying here is just that if you are given two numbers, you can find their greatest common divisor. In their greatest common divisor is just the number which gets into those numbers, but that number is their maximum or is their greatest. So maybe you can say 20 can have, maybe you can have 20 and 40, and 2 can get into 20 and 40. Even 5 can get into that. Even 10 can get into that. But is it the greatest common divisor? That's the question. Is it the greatest common divisor? I'm sure you are all seeing my screen. I'm sure you are all seeing my screen. Right? Someone to confirm? Okay, it's okay. Thank you for that. Okay, so I'm just saying the greatest common divisor of A and B is just the greatest number which gets into A and B without leaving a remainder, just like that. So the greatest common divisor of 30 and 105 is what? Is 15. This is the greatest number which gets into both 30 and 105, just like that. So there's an algorithm that we normally use to find such a number. And that algorithm is the Euclidean algorithm. So the Euclidean algorithm is a way to find the greatest common divisor of two positive integers. So we use it to find the greatest common divisor of what? Two positive integers called A and B. So the formal description of the Euclidean algorithm is such that there is going to be the input. And what is this input? The input is just the two positive integers, A and B. So you are just going to be given two integers, A and B. And then the output that the algorithm must produce is G, which is our greatest common divisor of those constants or of those integers that were given the A and B. So what you need to understand is the internal computation of this algorithm. The internal computation of this algorithm is the one that you need to understand. So if A is less than B, exchange A and B. In other words, if you are given a question which will be asking you to find the GCD of A and B, like something like this. This is our A and B. So if you are given such a question, you need to look at these values. In other words, we are saying if A is less than B, you need to exchange those values. So if A is less than B, you need to exchange those values. So in other words, the A must be always greater than B. A must be always greater than B. So if A is less than B, exchange A and B. So your B will become your new A and your A will become your new B. So divide A by B and get the remainder. So the next step is to divide A by B. That's why we want A to be always greater than B. Because the next step you are supposed to divide A by B and get the remainder. So you divide this one by B and you get the remainder. And this remainder R, if that remainder is equal to 0, you report B as the GCD of A and B. Let's make sure that you mute your mics. Sure, there's a mic which is giving some feedback. Let's make sure that we are all on mute. I'm sure it's Moses. Moses, I know. Let's make sure that we mute ourselves. Thank you. Yeah, they'll. I've actually put some headphones on, so yeah. Even the little sound, you distract me because I'm using headphones. Okay, thank you. So we're saying if R is equal to 0, or if you get the remainder 0, you need to report B as the GCD of A and B, which means your B will be the GCD or the greatest common divisor. Else replace A by B and replace B by R, return to the previous step. I think you can get this when you're actually doing it, when you're actually doing an example, but it's just very simple. You need to replace A by B, and then you replace B by the remainder that you got, and then you return to the previous step, which is this one of dividing A by B. So this is just an example which says compute the GCD of 210 and 45. So if you look at these two values, or these two positive integers, you need to identify which one is your A and which one is your B. So this one is going to be our A because this is the largest number, and then this one is our B. So we are going to find the GCD of A and B, where our A is 210 and our B is 45. So the first step was to exchange if A is less than B. But here I'm sure we are good to go. And then the next step, you need to divide A by B and get the remainder R. So you need to divide A by B and you get the remainder R. So you need to divide 210 by 45. And 210 divided by 45 is 4. It's 4. That's why we have got this 4 times 45. 4.45 is just the same as saying 4 times 45. It's just like 4 times 45 plus 30. That's what we have here. So we are saying 45 into 210, we are going to get a 4, and the remainder is what? The remainder R that we are looking for is 30. If you say 4 times 5, then minus 210, you are going to get a 30 as your remainder. I'm sure if you do a quick mathematics there, you find out that 45 into 210 is 4, and the remainder will be 30. So this whole thing is from this step. It's from this step. So it's like we are expressing this result in terms of 210. If you solve this one, you get this 210. You are saying it's 4 times 45 plus 30. You are going to get 210. So I'm sure you are seeing where we are coming from. So the next thing to do, you check if the remainder is equal to 0. But here the remainder is what? The remainder is 30, so it's not equal to 0. Otherwise, we are going to report B as the GCD. Otherwise, we are going to report, I was trying to add someone, okay. So otherwise, we are going to get the B, which is 45, as our GCD, but no. So what do you do there? You go to the next step, which says replace A by B and replace B by R. So you need to replace A, which is 210, you need to replace it by B, which means our new A will become what? 45. And then replace this B, which was 45, by R, and our R, which is the remainder here, is 30. So you need to put 30 here. So end up having 45 and 30. So now you need to find the GCD of 45 and 30. So to find that, you need to divide 45 by what? By 30. So it's 45 divided by 30. And it's what? It's a 1 and a remainder of 15. That's why we have got 1 times 30 plus 15. That's why we've got 1 times 30 plus 15. So this one will give us a result of what? Of 45. I'm sure this is just a simple mathematics. Is it not clear? on this statement, on what we mean on this statement. Just want the feedback. Is it not clear?
Yeah,
It's
it's
clear,
clear.
sir.
More than clear, sir. More than clear.
Okay, it's okay. So that's what
It's
we
clear.
get there. Okay, so that's what so we are just expressing this 45 in terms of this 30 and the remainder. So 13 to 45 is 1, and then remainder 15. So if we say 1 times 30 plus 15, we are just going to get 45. And then next, since our remainder 15 is not equal to 0, so we are going to replace A by B and then B by R. So our A was 45, and then we are going to replace it by B, which is 30. So that's why you have a 30 here. And then our R was 15, and then we are going to replace B by what? By 15 here. Then next, you are going to find the GCD of 30 and 15. So you are going to say 30 divided by 15, and you get 2 remainder 0. So our R now is what? It's 0. Our R is now what? 0. So we are going to get 2 times 15 plus 0. So whenever you get your remainder as 0, you were supposed to report B as your what? So return to the previous. Okay, so you are supposed to report B as the greatest common divisor, and your B is what? Is 15 here. So you report this B as your what? As your greatest common divisor. That's how you use the Euclidean algorithm to find the greatest common divisor of two integers. I don't know if there are questions here on finding the GCD using. So if we do not have questions, let me move on to this. Such type of equations, sometimes you'll be asked to solve these equations using the Euclidean algorithm. So application of solving equations of the form ax plus by is equal to c. So find the values of x and y given that 182x plus 247y is equal to the greatest common divisor of 182 and 247. So whenever you encounter such questions or such problem, you need to see that first you need to calculate the greatest common divisor of 182 and 247. And then next you use that result to find the value of x and y. So in other words, you are being asked to find the GCD of these two numbers, and then later on you are being asked to solve this equation. So how do you do that? The first things first, let's find the GCD of 182 and 247. But before doing that, look at this. Your A is less than B, so you need to interchange this. Replace A by B and B by A. That's why you have the GCD of 247 and 182, just like this. It's because A is less than B. After that, I need to to divide 247 by 182. And if you say 247 divided by 182, you are going to get 1 and a remainder of 65. And a remainder of 65. So this is our remainder. So if you just say 1 times a 182 plus 65, you are just going to get this 247. All right. So since our remainder is not equal to 0, we are going to replace our a by b and b by r. So we are going to replace this 247 by 182 and b by the remainder, just like that. So the next thing is to divide 182 by 65, which is going to give us a 2 with a remainder of what? Of 52. So our remainder now is 52, and this 65 gets into 182 two times. So if we say 2 times 65 plus 52, we get this 182. That's where this expression is coming from. And then the next thing, since our 52 is not equal to 0, you need to replace this a by b, which is this 65. And then you replace this b by our remainder, which is 52. And then the next thing, you divide 65 by 52. which is going to give us a 1 and a remainder of what? Of 13. That's why we have got 1 times 52 plus 13. So since our remainder is not equal to 0, you need to replace your A by B, which is this 52 will become your new A, and the B, which is 13, B will be replaced by the remainder, which is now 13. Then the next thing is to divide the 52 by 13, and we are going to get a 4 and a remainder 0. So whenever you get a remainder 0, report your B as the greatest common divisor. So this is our B. We report that as the greatest common divisor, or just taking the last remainder that you have. So the GCD of this one is 13. The GCD is 13. So in other words, now you'll be asked to solve 182x plus 247y is equal to 13. So this was the first part of it. Now what you need to do is to solve 182x plus 247y is equal to 13. How do you do that? You need to reverse the algorithm. You need to reverse the algorithm so that you can end up having an expression in this form. So please, when you are doing this, try by all means not to multiply things. And not to multiply things. Try by all means. Treat some of the terms as maybe x and y, things that you cannot multiply, like the way you add algebraic expressions and the way you multiply algebraic expressions, something like that. So by using the reverse algorithm, you start from the last step. You start from the what? From the last step. So if you look at the last step, we are having 13 is equal to 65 minus 1 times 52. Where is it coming? We are now expressing this remainder in terms of this value and this value. Remember, on this one, we are just saying 65. So I'm using a mouse. My computer is not a touch screen, so I'm using a mouse to write. So yeah, I'll be a little bit slow. Yeah. So I'm saying 65 is equal to 1 times 52, 1.52 plus what? Plus 13. So if we look at this one, remember we have got an equation which says 182x plus 247y is equal to 13. Okay? So it means we can make this one the subject of formula and then have at least something which is most likely go in the right direction. Remember, if 182x plus 247y is equals to 13. So let's leave 13 on its own side and push everything to the other side. So from this step, I'm sure we can confirm this is what we have. So we can take this one to the other side. So if we do so, we end up having 65 minus 1.52 or 1 times 52. We are taking this 52 maybe as a variable like a. So we do not multiply that. So it would be 65 minus 1 dot a or 1.52. So we are taking this one as a coefficient of this one, something like that. So that's why we have 13 is equal to 65 minus 1.52 or 1 times 52. So once you are done with this step, you see we have used this step. So the next thing is to use this step, is to use that step. So if you look at this one, we are going to have 65 minus 1.182 minus 2.65. We have replaced this 52 with something else. How? Because we have actually made this 52 the subject of formula again. So you are making the remainder always the subject of formula, and then you use it to replace on the previous step. So if you look at this, we are saying 52 is equal to what? Is equal to we're having 182 is equals to this thing. we're having, okay, let me just, we're having 182 is equal to 2.65, maybe plus 52. Then from here, I want to make this 52 the subject of formula. This remains the subject. So you just take everything to this side. So end up having 182 minus 2.65 or 2 times 65. This is the thing that we have. And then you replace this 52 with the 52 value that we have, which is 182 minus 2.65. Once you have that, you can actually reduce this one to its simplest terms by multiplying with this coefficient. Remember, this minus 1 is multiplying everything. So that's why you see that we are having minus, this minus 182 is from minus 1 times 182. So that's why we have minus 1.182. We are maintaining this coefficient because they are very important. And then if you multiply minus 1 times minus 2.265, you are just going to get positive 2.65. That's why we are having this one. And then you add with this 65, it's as good as 1.65, because the coefficient of this one is 1. So if you add 2.65 plus 1.65, you are going to get 3.65. It's as good as we are just saying maybe 2a plus a. So you get a 3 what? A 3a. I'm sure we are all together here and we all agree. 2a plus 1.a or plus this a. So the coefficient of a is just 1. It is silent there. You can choose to leave it, but it's good just to put it there. So that's why we are getting this 3.65. Then from there, you have this one, minus 1.182 plus 3.65. So you see now we have this 182, maybe you are left with this 247. So there's still another step to use. So after using this step, you are left with this step. So what you need to do now is to make this 65 the subject of formula there. Need to make, so I just want to wrap maybe everything. Okay, so what you just need is to make that the subject of formula there. It's very simple. You have 65, so you have 247. So you have 247, which is equal to this thing 1.82, 1.182, maybe plus 65, right? Plus 65. This is 182 plus 65. So you want to make 65 the subject of formula. So you take this one to this side. So end up having something like 247 minus 1.182, something like that, which will be equal to 65. So this is the thing that we are going to use here. That's why you see you have got 247 minus 1.185. So you are going to replace this 65 with its equivalent value that we got from that step. So after expanding this, you end up having 3.247 minus 3, because if you say 3 times 1, you are going to get a negative 3 here. So it is going to be minus 3.182. So if you actually say minus 1 minus 3, you are going to get this minus 4. And then this is just positive 3. So you are going to get 3.247 minus 4.182 is equal to 13, is equal to 13. Remember, there is a 13 here. So you end up with something like 13 is equals to, remember, 247 y. 247 was the coefficient of y. So this is, that's where you get the value of y. And then 182x, which means 182 was the coefficient of x. So that's where you get the value of what? Of x. So the coefficient of 182 is the value for x. So x is equal to minus 4. and the coefficient of y is the of 247 is the value of y, which is equal to 3. There is a hand by Thomas. Do you want to say something? Do you want to contribute? Do you want to ask? Well, there was a hand by Thomas. Maybe it was earlier, so I didn't see it, but there's still a hand on Thomas Nyamuti. Thomas Nyamuti. Okay, you can unmute yourself. You can unmute yourself.
Can you hear me, sir?
Yes.
Good afternoon.
Afternoon, how are you?
I'm fine, sir. Thank you. I'm enjoying the lesson, but can you do us a favor, sir, by changing the color from yellow to green for the sake of legibility?
Okay. It's okay. Thank you.
Thank you for your comprehension.
Okay. Okay, Tim. So I don't know if I've got some questions on this one on how you can use the Euclidean algorithm to solve such equations of this type. So to solve equations of this type. If I do not have questions or contributions, I'm sure I can move on to the next topic, which is counting. And we are going to do the permutation and combinations. Permutation and combinations. So on the part of GCD, that's all what you are going to see maybe in your exam. That's all what you're going to see. So it's just a matter of practicing, maybe more examples, maybe doing 3 to 4 examples, you just master it. So let's just look at the counting topic. I'm just trying to add someone, okay? So let's talk about the permutation first. So a permutation of any distinct elements x1 up to xn is in order of the n elements x1 to xn. What you are saying here is that whenever you have got some distinct elements and you are asked to find the ways you can order them, maybe given any elements, the permutation is actually mainly focusing on the issue of order, the way you are going to order your things. So, for example, there are 6 permutations of 3 elements. If the elements are denoted A, B, C, the 6 permutations that you can create or the number of ways you can order the elements are these ones that we have, which is ABC, ACB, BAC, BCA, CAB, and CBA. So mostly on permutations, we are mostly looking at the way we can order the elements. Maybe you are given books and you are asked how many ways you can order these books, or how many ways you can arrange these books. Whenever, if the order matters, know that you are dealing with the what? With the permutation. You are dealing with the permutation. So ABC and ACB, these are two different permutations. Gift Sokir, may you please mute yourself, unless if you want to contribute something. Okay, thank you. So we're saying this ABC and ACB, these are two different things. BAC and BCA, these are two different things. You are going to see if it is a combination. This one is going to be maybe just the same as one thing. You can count it maybe as one thing because the order doesn't matter. But here we are saying the order does matter. So the number of permutation of any elements, you can use the formula n factorial. If you are asked to find the number of permutations of any elements, so the total number of permutations that you can get, instead of listing them, you can ask you how many of them that you can create from this total number of elements. So by giving the elements, you can just maybe try to arrange them, but there is a formula which can actually give you the total number of permutations that you can generate, and that formula is n factorial. So there are 24 permutations of objects. Like here, we are given 3 objects or 3 elements. So how many permutations you can create? So there are 24. So this one is an example which is not coming from this example. It's different. So you are being asked, maybe you are given 4 elements and you are asked to find the permutations or the total number of permutations from those elements. The result is 24. Why? Because you just find the factorial of what? Of 4. So 4 factorial is the multiplication of 4 made by 3, by 2, by 1. That's how you find the factorial of a number. I'm sure this one is a very basic thing. If you are saying any factorial, you start at the value n, multiplying by each and every integer after decreasing it by 1, till you reach to 1. And also take note of that 0 factorial is always equal to 1. 0 factorial is always equal to 1. So if you want a factorial of a number, if it is 4, it's 4 times 3 times 2 times 1. If it is 3 factorial, it's 3 times 2 times 1. If it is 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1. If it is 0 factorial, the answer is always 1. Let's know that. So in some cases, we need to find the number of permutations of any elements taken at a time. So sometimes you might be given maybe 20 elements in your set, and you'll be asked to create maybe permutations of maybe 5 of elements of those elements, but those permutations maybe you'll be asked to have 5 elements at a time. So if you are given such type of questions, you need to use this formula, which says P of nr is equals to n factorial over n minus r factorial. What is n? What is r? So here we are saying if 1 or if r is greater than or equal to 1 and r is less than or equal to n, then the number of permutations of any elements taken r at a time is n times n minus 1 times n minus 2 dot up to n minus r plus 1. So the number of permutations of any elements taken r at a time is sometimes denoted as p of n r or npr. So n is the number of elements. R is the number of elements which should be in the permutation that you want to create, just like that. There was someone who was complaining or not seeing anything. I think it's Jermaine Nyandor. Is it the same with the others on the chat?
Yeah, no, the screen is very clear.
Okay, so if you face that challenge, I think the easy way to fix, just log out and try to log in. I'm sure when you just log in, it will just try to fix everything for you. I don't know the other way around. I'm sure you can research on that. Yeah, that's why you are students. Can research on that. I'm sure there is a better way to fix that rather than to go out of the meeting and then rejoin. Yeah, there's always a solution.
But
So,
I've tried 3 times.
and it didn't work.
Yes.
And you are seeing nothing.
I am seeing nothing.
What? I don't know. Okay, let me just try to reshare. Let me just try to reshare the slide.
Thank you, sir. I'm seeing. Yeah, okay. Now I can see it.
Okay, it's okay. So the issue is that you need to be able to identify your n and your r. The n is just the elements, the total number of elements in your set that you are given. And then the r is the number of elements which should be in your each and every permutation. So like here, how many 2-letter words can be formed from letters in the set A, B, C, D, if repeated letters are allowed. So if you look at this one, this is where you get your N. And then this is where you get your what? Your R. How many two-letter words can be formed from letters in the set A, B, C, D if repeated letters are allowed? So instead of doing all this, you can just use the formula P of n r, which is equals to n factorial over n minus r factorial. Your n is 4 because we've got total number of what? Of 4 here, elements of 4. So it's 4 factorial over 4 minus r then factorial, which is 4 minus our r is 2. So it's 4 minus 2 then factorial. So you end up having a 4 factorial over 2 factorial. And you know that 4 factorial is 4 times 3 times 2 times 1. Then you divide it by 2 factorial, which is 2 times what? 2 times 1. And then this part can cancel each other. And you left out with what? With 4 times 3, which is going to give you a 12. So that's how you can find the total number of permutation. And then there's this exercise. How many ways can 5 of the letters of the word algorithm be selected and written in a row? So if you look at this one, you are given the word algorithm. And then you are given 5 here. How many ways can 5 of the letters of the word algorithm? So here, that's where you get your N. And then here, that's where you get your what? Your R. And then you plug it into your what? Into your formula. So you have to actually count the letters on the word algorithm. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 9. So it will be 9 factorial over 9 minus 5, since our R is 5 factorial, which will give you maybe this 5 factorial will cancel each other with the remainder of this part of 9 factorial. So you just say 9 minus 5. What do you get? 9 minus 5 is 4. Okay, so the 4 factorial, you cancel each other with the 4 factorial of this part. I'm sure you will see it, because it was supposed to be over 4 factorial here. But we are saying 9 times 8 times 7 times 6 times 5. 4 factorial is just 4 times 3 times 2 times 1. So it was just going to cancel each other with the remainder of this 9 factorial here. And this is going to be the answer. So you are going to get 1,500, so 15,120 permutation of 5, which can have 5 letters each. That's like that. So how many ways can 5 of the letters of the word algorithm be selected and written in a row if the first 2 letters must be TH? So if you look at this one, you are given the first 2 letters as TH. So in other words, you know the first 2 letters of every permutation that you want to create. And the total must be what? Must be 5. So in other words, you are remaining with finding the next 3 letters, right? What the question says, how many ways can 5 of the letters of the word algorithm be selected and written in a row if the first 2 letters must be TH? So how you can handle this one? So since the first 2 letters must be TH, hence we need to choose the remaining 3 letters out of the left 9 minus 2, which is 7 alphabets. So if you look at that, we already have the 2, which is the TH. So you are left with only what? 7 from our N. If you look at the end of our N is now 7 because we've actually already taken the 2 out and you already know where they are going to be placed. So we are left with what? With the 7. So now we are saying 7. And what is our R? We are taking 3 at a time because we already have these 2. Want to make them 5, but we already have these 2. So we are taking 3 at a time. That's why we have our R as 3. Then it's 7 factorial over 7 minus 3 because it's n minus r there. Then we find the factorial of that. So it's just 7 factorial over 7 minus 3 is 4 factorial. So the 4 factorial part here and the one which is at the denominator will cancel each other out, and they need to be 7 times 6 times 5. So you end up having 210 ways. You end up having 210 ways. So that's it on permutation. I don't know if I've got some questions on permutation. Okay. So let me talk about the combination. Let's look at the combinations. So a combination of n elements x1 up to xn taken r at a time is the selection of r elements where order does not count. So here order does not what? Does not count. So there are 4 combinations of 4 elements taken 3 at a time if the elements are denoted A, B, C, and D. The 4 combinations are ABC, ABD, ACD, and BCD. If you try to write maybe ACB, ACB is the same as ABC because the order doesn't matter. So you're just going to have maybe ABC, and then maybe ABD, and maybe ACD, maybe BCD, something like that. You cannot have BAC here because we are just saying it is just the same because the order doesn't matter. So on combination, the order doesn't matter, but on permutation, the order does matter. So the number of combination of any elements taken r at a time here is actually n factorial over r factorial and n minus r factorial. So we are just saying from the previous formula that we were using, this one, we are just going to divide it by r factorial. We are just going to divide it by what? By r factorial, which is going to be like we are multiplying it. Okay, maybe it's just like we are multiplying it by what? By 1 over r factorial. So it is just going to be fixed here at the denominator. We're just going to put it there at the denominator. So instead of having n factorial over n minus r factorial, it is just going to be n factorial over r factorial times n minus r factorial. That's the way you can find the total number of ways or the combinations. So how many committees of 3 can be formed from 7 people? So if you look at this one, we've got 7 people and you want to form a committee of 3 people. So how many ways can we do that? Here the order doesn't matter. Which one are you going to first select? Okay, so the order doesn't matter. If you select executive, you've actually selected executive. The order doesn't matter that you have selected this group of 3, but you started by this one. But the contribution of those people is just going to be the same because they are the same people. So the order doesn't matter. If you started by selecting me and then select the other 2, it's not going to be different when you just started by select someone and then you selected me at the second option. So that's what it is on combinations. The order doesn't matter. So here you are asked to select a committee of 3. So we want to see how many can we form if we have got 7 people, but how many combinations then that we can come up with from those 7 people. If you want to have a group of 3, how many possible combinations? So the best way to answer that, you use this formula, which says n factorial over r factorial times n minus r factorial. So each commit is a combination of 7 people taken 3 at a time. That's the number of committees that can be formed is 7 factorial over 3 factorial times r minus 3 factorial. So I think this is just basic simple. It's just basic mathematics. 7 minus 3 is 4. So it's just going to be 3 factorial times 4 factorial. Then here's 7 factorial. So this part is going to cancel. This whole part is going to cancel each other. This one. So end up having 7 times 6 times 5 over 3 times 4. And then the result will be what? So maybe this part will cancel each other. I'm just trying to show you the best way you can actually cancel all these things. So you can answer this 3 times 2 is 6. So you can cancel this 6 and this 3 times 2. So end up having 7 times what? 7 times 5, which is what? 10 divided by 2. I think I missed something there. So this 2, is it supposed to be here? This 2, I'm sure this was supposed to be a 1. This one, it's wrong. This one is supposed to be a 1. Because it's 3 factorial. 3 factorial is 3 times 2 times 1. So this is just a mistake. So it's 3 times 2 times 1. So if you cancel this one, you end up having 7 times 5, which is 35. So you find out that you don't need even to use a calculator here if you do it very well. So the combination of n elements taken out at a time is sometimes denoted as C n R, or n choose R. Okay. So I don't know if I have got some questions on combination and permutations, or some contribution. Maybe someone want to contribute something. Okay, if there's no hand, you can proceed to the pigeonhole principle. Let's look at the pigeonhole principle. So the pigeon principle is a mathematical principle that states that if any items are put into K containers with n greater than K, then at least one container must have or must contain more than one item. I'm just saying we've got some containers n.
Hello, sir.
Okay,
Hello. Sorry,
yes.
I couldn't raise the end. I have a question on permutations. I think I just sent the question more to chat.
You have a question, you can ask.
Okay. I was just asking, may you please help us code panel that question? It's just a single question. Let me read the question. How many ways can the letters of the word leader be selected while keeping the vowels together?
Leader.
Yeah, it has got like a repetition of some letters, sort of.
Okay. If it have got some repetition, you divide by the total number. Like if there are words which are repeating, what you do then? You divide by the total number. Let's say we are saying O is repeating 3 times. So you just divide by 3 factorial. If there is another letter which is repeating maybe 5 times, you divide again by 5 factorial. So maybe if you have, maybe I can say if you have got 3 letters which are repeating, what you just do there, you divide, you just count the total number when it is repeating. So maybe if it is the first letter is repeating 3 times, you just say 3 factorial. If the other one is repeating by 4 times, just say 4 factorial. If it is the other one is repeating by maybe two times, just say 2 factorial. So in other words, you put this one at the denominator, you multiply this one. 3 factorial times 4 factorial times 2 factorial, then you put it on the what? On the numerator, and you just get your answer. And you just get your answer then. Yeah. It's very
okay.
it's very simple. It's very simple. If you look at that one, that's the very simplest question that you can have on permutation. You just need to do a quick research on that one. You just divide it by the total number of the repetition, total number of the repetition, yes, and you just put a factorial. If it is repeating 3 times, just 3 factorial. If it is repeating 4 times, just 4 factorial. So you multiply those repetitions. If there are 3 letters which are repeating, so the total number of repetition of the first letter with a factorial, you multiply with the total number of the repetition of the second letter with a factorial, you multiply with the total number of repetitions with the factorial of the other letter. And that total is the one that you are going to put on the numerator.
Okay. So the statement that keeping the vowels together, it's like, I think it will be affecting our value of n.
You come back to this th. Yeah, you come back to this th. You are already given th.
Hello?
You come, it's just like this question that we've done, which says algorithm. You are saying you are given that the first 2 letters are th. So it's just as good you are being told that the vowels are going to stay together. So you have actually given the order that the vowels are already selected and they've got the same order. They are going to be together, just like this TH that we have. So in other words, maybe you're just going to start with those vowels and you are just going to sort the, you're just going to take those which are remained. So if it was leader, if you look at this one, it was leader, right? So I think you have to take this score. You have to take this score. Sorry. Okay, I'm back. Okay, what I was saying is you are being told that these vowels are already ordered, which means that you are going to have you're going to have maybe this E, E, A, and then you are being asked to sort the remaining, which is L, D, and R. This one, L, D, and R are the remaining one. So this question is just as good as this question that we have done, where you are already given that TH is going to be the first one. So I'm sure it's going to be easy for you to deal with this question. I'm not going to give you the answer. I'm sure.
Yeah,
you,
it is.
yeah,
Now I get it.
Yeah. So what you just need to do maybe is just to do a little research there, and then you get the answer.
Okay, thank you, sir. That's interesting.
Okay. Then what else? Okay, we're on the pigeonhole principle. We were saying the pigeonhole principle is a mathematical principle that says that if any items are put into K containers with any greater than K, then at least one container must contain more than one item. So in other words, we are just saying we've got K containers, right? And we've got n pigeons that we want to put into those containers. Once, if the number of pigeons is more than the number of K or the number of containers, you are always going to get a container which is going to have at least one, or which is going to have at least one pigeon, or more than one pigeon. I think it's self-explanatory. Like if you have 5 containers and you have got maybe 7 pigeons that you want to put into container, taking that maybe we are going to spread them one. It's just self-explanatory that we are going to have a container which is going to have more than one pigeon. So that's the principle. Whenever you've got containers which are less than the number of things that you want to place into those containers, there is going to be always a one container which you have at least one or more than one pigeon. Just like that. So that's the principle. If you ask for the definition, that's what you give there. Yeah, because it's very basic, but maybe we just wanted to see how, or are you able to just elaborate the principle as it is. So if any pigeons fly into K pigeonholes and K less than n, some pigeonhole contains at least 2 pigeons. This is just like the repetition of the definition. This is just an example. For example, here 10 people with first name Arnold, Ben, and Alan, and last names it's Razambo, Farhan, and Moy. Show that at least 2 people have the same first and last names. These are kind of the questions that will be asked in your exams. And it's very simple and very straightforward, but maybe it's just the technicality. We are saying 10 people have first name Arnold, Ben, and Alan. So we have got 10 people with those first name Arnold, Ben, and Alan. and the last names Razambo, Farhan, and Moyo. So we have such 10 people. And you are supposed to show that at least 2 people. Okay, okay, just so I'm back. Okay, so I was saying you've got 10 people with the first name Arnold, Ben, and Alan, and the last names is Razambo, Farhan, and Moyo. And you are being asked to show that at least 2 people have the same first name and last names, just like that. So how do you show that? How do you show that? It's very simple. It's like if you take the combination, this Arnold, if you just take the combination of Arnold, Farani, maybe you are going to have the person called Arnold Razambo, Arnold Farani, and Arnold Moyo. So we've got those 3 people. And then next we have Ben Razambo, Ben Farani, and Ben Moyo. It's now 6. We can have Alan Razambo, Alan Farani, and Alan Moyo, which is going to be what? 9. There. Do we still have any other combination without repeating those names? If you look at that, was this Arnold, this Benny is actually paid with everything. This Alan is paid with everything. And after that, we've got 9 people with the different names, with the different name and last names. So those are the people that you can uniquely identify. But if you try to add another person with the combination of Arnold, either with those or Benny with those, you are repeating. So it is evident that there's going to be at least 2 people which will have the same first name and last name. So that's what you'll be asked to prove. So there are 9 possible names for the 10 people. If we think of the people as pigeons and the names as pigeonholes, we can consider the assignment of names to people to be that of assigning pigeonholes to the pigeons. So by the pigeonhole principle, some name which is pigeonhole is assigned to at least 2 people which are pigeons, just like that. Just like that. So it's like that's how you answer this question. You just need to show that whenever I assigned these names to these people, I'm just going to have 9 names, 9 different names for 10 people. So it's evident that whenever I try to add another name, I'm going to have 2 people with the same what? With the same name. At least 2, it means greater than or equal to 2. So you will be having at least 2 people with the same first and last names. Are we clear on this one?
Yes, I think you are clear.
Okay. Then this one is another example which says among any group of 367 people, there must be at least 2 with the same birthday because there are only 366 possible birthdays. So maybe you'll be asked, how many people do we need for us to have at least maybe 2 people with the same birthday? That will be the question. So you know that for you to have at least 2 people with the same birthday, for it to be possible, that it is evident that it is going to be possible to have those people, is when we have 367 people going above. Why? Because we have got a year which have got 366 days. So if you allocate each and every person a day. And then if you try to add one person, that person is going to fall on someone's birthday. Hence, we are going to have at least 2 people with the same birthday. That's how you prove that. So in any set of 27 English words, there must be at least 2 that begin with the same letter, since there are 26 letters in the alphabet. So maybe the question will be, how many letters do we need, or how many words do we need to make sure that we have the words which will start with the same letter? So how many English words do we need to make sure that we have maybe at least 2 words which we start with what? With the same letter? And the answer will be 27. Why 27? Because we have got 26 letters in our English alphabet. So if you assign each word maybe A, B, C, D up to Z, saying this one is going to start with A, and then the next word until you reach to Z, you are going to have the extra word. That extra word is going to start by either an A or any letter which is from A to Z. And once we have something like that, that word is going to have the same initial, just like the other word. Hence, you have at least 2 words which you start with the same letter. So that's how you counter these questions. What is the minimum number of students in a class to be sure that 2 of them are born in the same month? What do you think on this one? What do you think on this one? Just want someone to explain this one. Yes, Dakarai.
Yeah, as for me, I think we should have 13 students, at least 13 students.
Why? Why
Hello?
at least 30? Why at least 30?
Anyone can hear me?
Yes. Yes, I can hear you.
Okay. 13, just because in the classroom, okay, we have 12 months, right?
Yes.
Just because we're dealing with the months, we have 12 months in a year. So we have to assign, if we have to assign each student a month, we'll have 12 students with the distinct month who are born in each distinct month, right? So for at least 2 students to share a birthday, to share a month, or to be born in the same month, there should be an extra student that falls out of the 12 students we already have. Because if we have the 13th students, he or she will be born in the month between January to December, which we've already allocated to other students, to other 12 students. So at least 1 month we have 2 students born in that month.
Exactly. Yeah, that's it. That's it.
Okay, thank you.
Thank you for the explanation. I'm sure vanenze vetse kunzwa vanzwa. Ndechida kutokhuluma but kunoita kuchindinetsa muzondibatsira kukhuluma. Those who can khuluma, please come to my rescue. Right, tinawo kwanokhuluma. Avachade kudavira. Maybe it's just because I'm not. Maybe it's just because.
Tiripo, we can kuluma.
Okay, so I need your help. Muita muchinyorwa manotes and it so that I can kuluma just like you. Okay, thank you. Anyway, this is the exercise which says let A is equal to this set with elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And suppose 6 integers are chosen from A. Must there be 2 integers whose sum is 11? So you are saying from this set, there must be 2 integers whose sum is 11. There must be two integers whose sum is 11. So how you can prove that? We are saying suppose 6 integers are chosen from A. So from every 6 integers that you are going to choose from A, there must be 2 integers whose sum is 11. So the set can be partitioned into 5 subsets. So in other words, you need to partition them into subsets so that you can show us that if you take these two numbers, you are going to have at least this option where you have the sum which will be giving us 11. So suppose 6 integers are chosen from A, there must be what? 2 integers whose sum is 11. So now on that one, how do you do that? In other words, you need to find the pair of numbers whose sum will give you what? 11 and list them. So you just look for all the possible combinations which will give you the sum of 11 from this set. Like if you get this 1 and 10, you get 11. If you get 2 and 9, you get 11. If you add 3, maybe 3 and 8, you get 11. 4 and 7, you get 11. 5 and 6, you get 11. So if you look at these sets, there are 1, 2, 3, 4, 5. Okay. So we are saying if you are going to choose 6 numbers, on those numbers must be 2 integers whose sum is 11. So each consistent. So how do you prove that? So it's like if you are trying to choose numbers from this set, you can choose the first 5. When you choose the next number, that number is going to have maybe one number in that set which is going to give us 11 if we add with that number. So these 5 subsets can be considered as 5 pigeonholes. You can consider this one as our containers, right? We are going to put the what? The pigeons. Then if 6 is equals to 5, and then 6 is equals to what? 5 plus 1 integers are selected from A. Then by the pigeonhole principle, at least 2 must be from one of the 5 subsets. So at least 2 must be from what? One of the what? Of the 5 subsets. But then the sum of these 2 integers is what? Is 11. So you can try to pick the numbers, the 6 numbers from here. The 6 numbers from here. Maybe I'll pick what? This 1, 2, and 3, and 4, and 5. If I pick these numbers, they are 5. Whenever I would try to pick the next number, that number you have a pair for it to become what? For it to become 11. So maybe I can pick this. Let me try to pick the least as possible. This 1 and this 2, maybe and this 3 and this 4 and 5. If we try to pick maybe this 8, I have already picked in 3. So I have a number that I'll pair with it, which will give me what? An 11. So this is how you prove that. This is how you prove that. So you need just to make pair of these numbers, which will give you the sum of 11. And then from there, you can pick the 6 numbers from this one, and then you prove that it is going to give you at 11. So maybe what is important is that it's just this explanation. That's the explanation that you have to give. So if the 6 integers are selected from this set A or from these subsets, then the pigeonhole, or then by the pigeonhole principle, at least 2 must be from one of the 5 subsets. But then the sum of these 2 integers is what? Is 11. Then hence what? Hence proven. Just like that. I don't know if you are answered before we move away from the pigeonhole principle. Also, do you have questions on the pigeonhole principle or contributions? It is good to ask questions. It is good to contribute. Just want to make it interesting, but if there is nothing to ask, I'm sure we are all satisfied with this topic. Let's look at proofs. Let's look at proofs. And this one contributes more on exams because I think ndosinoita kuti zvinhu zvifamba nditi ungagona kuprova even mulife zvinofamba nditi. I'm sure this topic constitutes of more subtopics. So that's why it have got more questions in your exams. Yeah. Also on methods of proofs, we have got a lot of methods there to ask, rather than if it is pigeonhole principle, it's just maybe 4 marks or just like that. If it is on combinations and permutation, maybe if it contributed more, it's just of 8 marks maximum. But with methods of proofs, you can ask maybe contradiction, contraposition, direct proof, indirect proof, proof by induction. You see, so maybe this one in the graphs, yeah, they weigh maybe 50-50. The other ones are just there to support so that we can get to what you are supposed to get there, maybe to 100% to 80%, just like that. So here you want to do, or want to look at what? It proofs, the methods of proofs. So on methods of proofs, we've got the direct proofs, we've got the indirect proofs, which branch further to contraposition and contradiction. And then we are going to start with the direct proof. We're going to start with the direct proof. So the implication, P implies Q, can be proved by showing that if P is true, then Q must also be true. This shows that the combination of P true and P and Q false never occurs. So you are saying the implication, if P implies Q, you are saying if P is true, then Q is also what? Is also true. I'm sure this was the stuff that we've done in the mathematical foundation. To those who disagree with me, you can disagree, but as someone who have actually taught you this module, mathematical foundation, I know we have covered this. Yeah. So we are just saying, we are doing some proofs there. We are just basically basing on the implication. If P is true, then Q is what? Is true. So I just maybe look in this table. If this one is true, then this one's true. If true implies false, it's false. And if false implies true, it means it is true. If false implies false, it means it is true. You are going to see with the methods that you are going to imply. Maybe it is contradiction, maybe it's just going to take maybe some of the values which are in here. Maybe it is, if it is contraposition, maybe you're just going to assume, okay, well, you're saying this is true and this is true, but yeah, I'm going to assume this is false, this is false. Maybe, so this is, maybe this, it will be this part that it will be using to prove. So in other words, when you're doing proofs, you are most likely looking at the implication. P implies Q. If this one is true and then this one is true. If this one is false and this one is false, it means maybe the supposition that you gave was what? Was true, something like that. So let's focus on the direct proofs. So there are some basics that you need to understand. Whenever you are doing direct proofs, there are some basics that you need to be well versed with. So an integer n is even if and only if n is equal to 2k for some integer k. This is the first basic that you have to know. For any number or for any integer to be said it is even, it must be of this form. N is equals to 2k for some integer k. So this k will be any integer. So in other words, it will be a multiple of what? Of 2 for it to be an even integer. So whenever you are said n is an even integer, it must be of this form. Maybe it's 2 times 2, which means your k will be equal to 2. Maybe it's 2 times 1, maybe it's 2 times 3, maybe it's 2 times 20 there, where your k is 20. That number which is going to be multiplied by 2 is always going to give us a what? An even number. So we are guaranteed that that number is going to be what? It's going to be an even number, just like that. So this is the first basics that you need to know. Then the second one is when an integer is odd. So when an integer n is odd, or an integer n is odd if and only if n is equals to 2k plus 1 for some integer k. For you to say that n is odd, it must be of this form. 2k plus 1. It must be of this form, 2k plus 1. Any number which will be in that form will always result into what? Into an odd integer. If you are having maybe it's 2 times 3, if you add a 1 to it, you are going to have an odd number. It will become 7. Maybe you are having 2 times 1 plus 1, you're going to get a 3, which is an odd number. Try it by any way you are going to try it. You're just going to arrive at a what? At an odd number, just like that. So that's the second one. You can go on to an integer. N is prime if and only if n is greater than 1. Whenever n is greater than 1, whenever n is greater than 1, and for all positive integers r and s, if n is equals to rs or r times s, then r is equals to 1 or s is equal to 1. So we are saying for a number to be said it is a prime number, that number must be greater than 1. That's the first thing. So in other words, we do not have a prime number which is less than 1, right? And for all positive integers r and s, if n is equals to r times s, then r is equals to 1 or s is equal to 1. Prime number inamba yakaita sei. What do you think is a prime number?
A number that can be.
Okay, Simbarash, you can.
All right. A prime number is a number that can only be divided by 1 and itself.
That can be divided by 1 and itself. Exactly. A gift, there is a hint. You can contribute or you can ask. You are muted, so you can unmute yourself and contribute. Gift, so gift.
Yes, I just wanted to define a prime number as a number that has got 2 factors only.
Okay, and which are those factors?
It will be 1 and itself.
Which is 1 and itself, right? Exactly. So this is why, that's why we are saying here, one of these will be what? Will be 1. Was that value or that number, for it to be a prime number, it must be divided by itself or by a 1. So whenever you have n is equal to r dot s, it's as good as one of these must be what? Must be 1, so that this one can be divisible by itself, can be divisible by itself or by 1. So in other words, this r will be equal to n, or this s will be equal to this one, where the one will be either 1 or something like that. That's the explanation which is here. Also, there is this one which says any integer any greater than 1 is a composite if and only if n is equals to r dot s for some positive integers r and s, with r is not equal to 1 and s is not equal to 1. Much of these, I'm not sure if you are going with the real numbers. R is rational if and only if r for rational numbers, those numbers which can express is what is a over b without, and then some that you can express as a over b, where b is not equal to 0. If n and d are integers and d is not equal to 0, then d divides n, written as d pipe n. This one, d divides n. If and only if n is equals to d dot k for some integers k. It's like we can say this number divides into this number. If you can have a number that you can multiply like 2k, 2 something or 3 something. Like here, if n is equals to dk, something like that. It's like you divide this one exactly without leaving a remainder. There is no plus something there, plus something for a remainder, something like that. In an integer, n is called a perfect square. I'm sure you know the perfect square. Those which give you a number that you, if you find a square root, you just get the direct, or the integer, you just get the integer. Those are the perfect square numbers. So in an integer, n is called a perfect square if and only if n is equals to k squared. So if you express it as what is k squared, you can say that this number is a what? This number is a perfect square. Those number with perfect squares, like 4, if you find the square root of 4, it's 2. If it's 16, the square root of 16 is 4. So those are the numbers that you are looking at. Okay, so this is the example of a direct proof. So on direct proofs, you'll be using these basics. But trust me, most of those that we are going to use are 1, 2, 3, maybe 5, maybe 6, maybe 7. Yeah, maybe. Yeah. Then prove that the sum of two odd integers is even. Prove that the sum of two odd integers is even. Yeah, being asked to prove that every time you add two odd integers, you are going to get an even number. That's what you are being asked to. And then you are supposed to use a what? To use the direct proof. So the first assumption for you is that let's take m and n as two odd integers. And then by definition of odd numbers, we know that for an odd number, it must be of the form 2k plus 1 from here. It must be of the form 2k plus 1. Must be of the form 2k plus 1. That's why I say m must be equal to 2k plus 1 for some k is an element of Z. And n is equals to L plus what? Plus 1 for some L is an element of what? Of Z. So we are saying this L is an integer. So we have these two different what? We've got these two different integers, odd integers that we want to add. I'm trying to add or to accept these people who are trying to join us. So please do not put your m as 2k plus 1 and your n as 2k plus 1. It is good you have actually adding 2 and a 2. You always get an even number there. But what you want to do, you want to add two odd integers. You just want to add two odd integers, right? Just want to add two odd integers, not one that odd integer you added. So if you get what? Yeah, that's it. We are just saying, just put these two different values here. Here put a k, here put an L, or you can put whichever variable you want to use here. But make sure that these are two distinct numbers, right? So now m plus n, which is the addition of what? Of two odd integers, will be equal to 2k plus 1, which is equals to then 2k plus 1 plus 2l plus 1. So you add the like terms. So you are just going to have 2k plus 2l plus 2, and then you factorize to end up having something like this. You have 2k plus l plus 1. So after having something like this, you want to prove that this result is an even number. You want to prove that this one is an even number. How do you prove that? Once you have factored out these two, you will have something like 2 times this one. 2 times this one. So any number multiplied by 2 is always an even number. From this definition, n is equals to k for some integer. Okay, so anything multiplied by 2 is always going to give us a what? An even number. So you can take this one as your r here. So you have 2r where r is equals to this one. Hence m plus n is what? Is even. Since we know that any number multiplied by 2 is always even. So that's how you prove by using the direct proofs. That's how you prove by using the direct proof. So I don't know if I've got some questions here on direct proofs. Some questions, some contributions. Let's contribute. Okay, raise your hand. Okay. If there are no contributions, you do them in your exam. I'm sure you do them. Definitely you do them. Proof by contradiction. Proof by contradiction. So a proof by contradiction is based on the fact that either a statement is true or it is false, but not both. Proof by contradiction is based on the fact that either a statement is true or it is false, but not what, but not both. Hence, the supposition that the statement to be proved is false leads to logically to a contradiction, then the supposition must be false. So in other words, you are saying, if you are saying this statement is true, it must be either true or false. So whenever we assume that, whenever you say it is true and then you assume it is false, the answer that we must get must lead to a contradiction, because we are saying it is either false or what, or a true value. So hence the given statement must be what? Must be true. So if it contradicts with what you have said earlier, then the given statement must be what? Must be true. So many theorems in mathematics are conditional statements like what we have said earlier. P implies Q. So the negation of the implication P implies Q is P and the negation of what? Of Q. Thus, to prove an implication P implies Q by contradiction method, we suppose that the condition P and the negation of the conclusion Q is true and ultimately arrive at what? At a contradiction. So yes, you are given that P implies Q, then what you are going to do, you are going to negate the Q. You are going to negate the Q and you try to prove that. And it must lead to a contradiction. Remember, we are saying it is going to be true, and then you are saying it is going to be false. So prove that it is going to be false when you say that. But someone is saying it is going to be true. So it must lead to a contradiction. And then if it leads to a contradiction, then it is going to be what? It is going to be true. Let's see how we can do this. So this proof by contradiction, maybe it can be summarized as suppose the statement to be proved is false, right? The first thing you have to suppose that the statement to be proved is false. Then you show that this supposition leads to logically a contradiction. Then you conclude that the statement to be proved is what? Is true. So that's what you do. So these are the steps that you need to go through. Maybe if we do an example, maybe it will be clear to you what do you mean by contradiction. So give a proof by contradiction for the statement. If n squared is an even integer, then n is an even integer. So I want to add someone here. So you're saying, prove that if n squared is even integer, then n is even integer. So your task is to prove that if n squared is even, then n must be also an even integer. That's your task, to prove this. So by contradiction, you are saying you need to negate this, and then you see if it is going to lead to a contradiction. Here we are saying if n squared is even, then n must be even. So suppose n squared is even integer and n is not even. That is, so that n is what? Is odd. Remember, here we say suppose the statement to be proved is what? Is false. Show that this supposition leads to logically to a contradiction. Logically to a contradiction. So the first thing is that you are being asked that whenever n squared is even, then n is also an even integer. But you say, no. If n squared is even, then n must be an odd number. That's what you want to what? That's what you want to prove. So what you do there, you take n as an odd number, and then you square it, and then you see what you are going to get, right? And then you see if it is going to lead to a contradiction. So suppose n squared is an even integer and n is odd, Hence, n is equals to 2k plus 1. Remember, from the basic steps, we have said that whenever we have got something in form of 2k plus 1, that number is going to be an integer. Is going to be an odd integer. So you square that. So n squared is going to be 2k plus 1 squared. So if you expand this, you're going to have 4k squared plus 4k plus 1. And then if you factor out 2 here, you are going to have 2 times 2k squared plus 2k, then plus 1. You can take this whole thing as an r. So you end up having a 2r plus 1, where r is equals to 2k squared plus 2k. So your n squared now will be equal to what? To this something which is of this form, which is a what? Which is an odd number, which is going to be an odd number. But remember, we're saying this one is what? Is even. You see where the contradiction is. You were saying if n squared is even, then n is what? Is an even integer. And then we just changed this one, or we negated this one, and we are saying if n squared is even, then n is odd. Then we've taken this one as an odd number, and then we have squared it to have n squared. After that, we end up having something which is an odd number, which is contradicting to the statement that we have said that if n squared is even, then n is odd, which is now contradicting to this statement. Once if it leads to that contradiction, then we can say that the given statement was true, that if n squared is even, then also n is an even integer, just like that. So this shows that n squared is odd, which is in a contradiction to our supposition that n squared is even. Hence, the given statement is true. I don't know if I need to clarify more on proof by contradiction.
Yes, I think. Hello.
Hello. Yes, I'm hearing. You can.
Yeah,
Can
I'm sorry.
Beetle.
Can you repeat? There's English jargon there. There's a lot of English there. Can you repeat again? Say sorry.
Okay, it's okay. Maybe let's look at this one on proof by contradiction. What do you mean when you say proof by contradiction? I think what you need to look at it, the way you need to look at it, you are given something said to be true, and then for you want to prove that that thing is false. On the way of trying to prove it, on the way of trying to prove that it is false, once that thing, if it is true, you are definitely going to arrive at a contradiction. Mumwe ari kuti chiri true, wewe wobva wataiwa no chiri false. Then along the process of proving, you must arrive at a contradiction. Because kana yanga ari true kana zvichiita true, obvious, chako chichadi, chako chicharamba. Kana chikaramba, zvakureva kuti zvonizvo, there is a contradiction. So the process just like that. You need, suppose the statement to be proved is false, right? And then when you suppose that it is false, then you prove that statement. By proving that statement, it will lead to a contradiction. The contradiction is that whenever it was supposed to be true, it is going to give you a false value. Then you can actually say that by contradiction, the given statement is true. Maybe I can just repeat this example so that you can see what I'm saying. If you look at this statement, give a proof by contradiction for the statement. If n squared is an even integer, then n is an even integer. This is the statement that you are given. So for you to prove by contradiction, you need to negate this given statement. In other words, you need to say, no. What you are claiming is false. Whenever n squared is even, n must be an odd integer. That's what you are claiming. Someone was saying, no. If n squared is what? Is even, then n must be an even integer. And you are saying, no, that one is false. So you are just saying, whenever n squared is even, n must be odd. It's now you are claiming that. And then what you do there, you put your n as what? as 2k plus 1, because you are saying, no, n must be an odd integer for you to get n squared as even. And then you square that n, and then you are solving this one, you are multiplying this one, you are expanding, and then after that, you are going to factor out 2 on 4k squared plus 4k. You are going to end up having 2 times 2k squared plus 2k, then plus this one, which is out of these brackets. So you end up having something of the form what? Odd, right? Which is 2r plus what? Plus 1. You see, but this value is for n squared. And remember, the first person was saying if n squared is even integer, then n is even. And we have claimed that, no, if n squared is even, then n must be odd. But your boys are n wako odd. N squared wako hana kubuda richi, hana kubuda ari even, abva abuda ari odd. That's the contradiction that we mean. Otherwise, they abuda ari even tighter, so the statement was false. But the fact that you have failed to prove that whenever n is odd, n squared is even. Hence, the given statement is what? Is true. I don't know if you are together now.
We are, sir. Thank you very much. Very clear now. Thank you.
Oh, okay. So maybe you can look at the proof by contraposition. Proof by contraposition. A proof by contraposition is based on the logical equivalence between a statement and its contrapositive. A proof by contraposition is based on the logical equivalence between a statement and its contrapositive. I'm sure if you remember, on mathematical foundation, we've talked about these things. A contrapositive statement. If you are given a statement and you are asked to give its contraposition or its contrapositive. So therefore, the implication P implies Q can be proved by showing that its contrapositive, the negation of Q, implies the negation of P is true. So like what we said in mathematical foundation, we have said if you are given P implies Q, the contraposition of that statement is the negation of Q implies the negation of P. So you need to actually show that. So you're just saying P implies Q. If P implies Q is true, the negation of Q implying the negation of P must be what? Must be true. So it's in other words, you are saying it must be true by going the what? The different direction. The negation of Q must be implied the negation of what? Of P. That's the proof by what? By contraposition. So the contraposition is usually proved directly. So the method of proof by contrapositive may be summarized as express the statement in the form if P then Q. Rewrite this statement in the contrapositive form if not Q then not P. Prove the contrapositive by a direct proof. So the contraposition is just as good as using direct proofs. But maybe what you want to get is how do you move from the implication to the contrapositive or to its contrapositive. If you are given P implies Q, the contrapositive of it is the negation of Q implies the negation of P. So that's what you need to do. After doing that, you just use the direct proofs, just as that. So prove that for all integers n, if n squared is even, then n is even. Now we want to use proof by what? Proof by contrapositive. So if the question is silent about the proof that you are supposed to use, we can use n. Can use what? N. But most of the question will tell you which one to use. So do not say I'm not going to do the contrapositive. I'm just going to do the contradiction. I'm not going to do this. I'm just going to do the mathematical induction way. No. Some of the questions we claim the method to use. So on the contrapositive of this statement, we are saying prove that for all integers n, if n squared is even, then n is even. We need to take the contrapositive first. So the contrapositive, so we are saying if n is not even, then n squared is not even. That's the contrapositive. You negate this, and you interchange them. Remember, the contrapositive of P implies Q. You negate this, and then you interchange them. So the negation of Q implies the negation of what? Of P. That's what we are doing here. We are saying if n squared is even, then n is even. So you are saying if n is not even, which means if n is odd, then this one is what? Is odd. So you negate this, and then you interchange them. So if n is odd, and then n squared is what? Is also odd. And then you prove that. If you manage to prove this statement, it means the original statement is what? Is true. That's how you do it. And the process is just the direct proofs. So here we suppose that n is what? N is odd. And we know that whenever n is odd, you have something like 2k plus 1. For some case, an element of set. So now n squared will be equal to what? You square this one. For you to get n squared, you square both the sides. So you end up having 2k plus 1 squared, which is was 4k squared plus 4k plus 1, something like this, right? After that, so that we just want to show it is a what? Is it the result will be an odd. You factor out 2 here, you end up having 2 times 2k squared plus 2k plus this one here outside here. And then what you have 2r plus r, where your r is equal to what? 2k squared plus 2k. So whenever you have something like this, it means that answer is a what? Is an odd integer. And remember, we've said if this one, if n is odd, then n squared is odd, which is true, right? So if this statement is true, or the contrapositive statement is true, it means the original statement was also what? True, or the given statement was also what? True. So that's your conclusion. Hence, n squared is odd. Thus, the contrapositive statement is true. And so the given statement is what? Is true. So this was the exercise proved by contraposition that if n is an integer, and then n cubed plus 5 is odd, then n is what? Is even. You can also do this one as part of your exercise. But do we have questions here on proof by contrapositive or contraposition, or some contributions? You can raise your hand if you want to contribute something, or if you want to ask. Story was zvakanaka kungotaura something, and tomboseka tetaita nekutaura so techiti mukambobvunza kana kuti if you just contribute something, yeah. Fun, but anyway, seems like you want to answer in your exams. Yeah, no rest. There's a hint.
I think can we get a live example where we apply this contradiction and contraposition? Real life examples where we need to apply this.
Okay. Where you can apply contrapositives. Maybe we can say on the proofs. Mostly, maybe you have a what? You have a proposition, right? You have a proposition that this one is going to be true, but you cannot actually ascertain that it is true unless if it is actually proved, right? Maybe you have a formula that you want to use. Maybe it's to calculate, what can we say? Maybe you want to calculate something. It's a formula that you want to calculate something. So you cannot ascertain that formula is true unless if you test the variables and the quantity of the coefficients there that you can use. So you can always use these methods of proofs to say that this one is true and then this one can work, this one cannot work. But I cannot actually pinpoint where you can just use this contrapositive. But it's just another way of proving by just going the other way around. If you look at the contrapositive, you are saying the statement, the implication statement and its contrapositive, they are always equal. They are always equal. So in other words, if you want to look if this one is equal to this one, or if you want to prove if this one is true, you can always use that opportunity that the statement and its contrapositive must be always equal. If something deviates from each other, it means that the component that I am testing is not true or is not going to give me something that I want. Maybe it's in a lab, you want to prove that. You can always use the contrapositive statement to prove if it is what, if it is true. I don't know if you are getting me there.
It's loud and clear.
Yeah. It's just that you have the contrapositive and the original statement. You can go through the contrapositive way. It must be the same by going through the what? The actual way of just proving, maybe by the direct proof, and then yeah, something like that. Anyway, then maybe the next thing is principle of mathematical induction. Principle of mathematical induction. I still have the energy. I still have the energy. Okay, let me try to do the principle of mathematical induction, and then for today to be enough. Maybe on our next tutorial we'll be doing the what? Maybe the graphs. Yeah, we do the graphs. Yeah. It will be enough for your exams. We do the graphs. So chimodipe energy. I've been talking continuous form.
Hello, sir.
Yes, Moses.
Yeah, I just wanted to assist no rest on a real life situation.
Yes.
About the contrapositive. It's like a statement like if it rains, the streets will be wet.
Yes.
Right. So if the streets are not wet, it is not rained. Okay. Things like that. Yeah. So it can actually be in the form of things like that, those statements. That if it rains, the streets will be wet. But if the streets are not wet, then it is not rained. Something like that.
Okay.
I think that's where we can actually apply the contrapositive.
Yeah, ndofunga panyatsokonesa. Hanzi mukakuona masitritsi akanyorovera mozoti kuri kunaya. Kuona kwamazoti hakusiri kunaya. So it's like the other way around, you are proving the same statement. You can either go the first way, that if it is raining, then the streets are wet. Okay, thank you for that. Thank you for that. Then on the principle of mathematical induction, given P of n, a proposition function, approved by mathematical induction, has two parts: a basis step, where we show that P of 1 is true, and an inductive step, where we show that for all positive integers k, if P of k is true, then P of k plus 1 is true. So okay, but what is very important, you get the message. So what I'm saying here is that we have the basis step when you are doing proof by mathematical induction, and we have the inductive step. So I'm sure that's what you have to master there. So in other words, a proof by mathematical induction is just a series of steps that you can follow to prove a proposition or function. So if it is a series of steps, you need to understand, or you need to master those steps so that you can prove the proposition or what function. So that is it either true or what, or false. So to prove that P of n is true for all positive integers n, where P of n is a propositional function, we complete two steps. The basis step, where we verify that P of 1 is what, is true, or we test the values in the domain, right, of n. And then if it is true for one of those values, then we move on to the inductive step, where we show that the conditional statement P of k implies P of k plus 1 is true for all positive integers k. So in other words, we will make an assumption that if it is true for any value in the for some value in this domain that we are given of n, it must be true for some other values like some also some arbitrary values like p of k. Also, so if it is true for that p of k, it must be also true for the next value, which is p of what? Of k plus 1. If you manage to prove that it is true for p of k and p of k plus 1, then you can actually ascertain that the given propositional function is what? Is true. So those are the steps. The basic step, then you give an assumption of p of k, and then you do the inductive step where you'll be claiming that if it is true for p of k, it must be true for p of k plus 1. And you prove that if it is true, then the given what statement is what is true. Or by mathematical induction, the given what statement is true, just like that. So this is an example which says use mathematical induction to show that 1 plus 2 plus 2 squared plus 2 to the power n is always equal to the power n plus 1 minus 1 for all non-negative integers n. So solution, let p of n be the proposition that 1 plus 2 plus 2 squared is equals to 2 to the power n plus 1 minus 1. So if you look at this one, you are adding or it's a summation of 2 to the power n. Like this one is just like 2 to the power 0, right? You are starting 2 to the power 0, 2 to the power 1, 2 to the power 2, up to 2 to the power n. So 2 to the power 0, it's a 1 here. And then this one is 2 to the power 1. And then this one 2 to the power 2, up to 2 to the power n. So I saying the summation of all this up to a certain number, we can get it by just having 2 to the power or something of this form, 2 to the power n plus 1, then minus 1. So that's what we want to prove. So how do you do that? So the basic step, you can look at p of 0. Why are we taking p of 0? Or when n is equal to when n is equal to what? Or when n is equal to 0. Because here we are saying for all non-negative integers n. So the domain is from 0 going up. So you can take any number that you can take, but just to take any which satisfies those values that we are seeing here. I think it would be actually appropriate, but I'm sure you can take any number. Once it is in this range, it is going to be true, because you're just going to put the value to the power n here, and then you put the value here, and then you tell us which one is going to give us the correct value. But I'm sure you need to take those, suppose you'll be adding them. So, okay, so base step p of 0 is true because 2 to the power 0 is what? Is equal to 1, right? 2 to the power 0 is equal to 1. And then 2 to the power 0 plus 1 is as good as 2 to the power 1, then minus 1, which is going to give you a what? A 1. This completes the basis step, because we've actually proved that whenever we have got p of 0, the left side will be equal to the right-hand side. What I was trying to explain is that let's take let's say we have put here 2. Let's say we've put our n as 2, p of 2. What were we going to get here? It was going to be 2 to the power 2 plus 1, which is going 2 to the power 3, then minus 1. 2 to the power 3 is what? Is it 8? Then minus 1 is 8. Then you are going to get what? A 7. So I'm sure, yeah, I'm sure some of you will get confused by getting this result of 7. Yet if you try to say 2 to the power 3, you get what? You get 8. Remember, here we are what? We are adding. We are adding here. So it's 1 plus 2 plus what? Plus 2 squared. What are we going to get there? What are we going to get? Because it must be equal to 7, the value that we are going to get there. So you are going to get what? This one. 1 plus 2 is what? Is 3. 2 squared is 4. So 4 plus 3 is what? Is going to be is going to be 7.
7.
It's going. If you look at it, we've taken our n as what? We've taken our n as 2, right? So if you take our n as 2, so this one is 0, this one is 1, then this one is 2. So we are going to add all these ones from here up to here. That's why we are getting 7 is equal to what? 7 is equal to 7. So you need to get this correct here on the basis step, on how you prove this one on the basis step. So it's a summation up to n. So we are summing everything up to where our n is equal to 2. So we are summing 1 plus 2. So it's like from 2 to the power 0 to the power 1 plus 2 to the power 1 plus 2 to the power 2. If we're going to put 3, we're going to add 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3. Then the result must be equal to something that we get here. So that's it on the basis step. Then on the inductive step, for the inductive step, I'm trying to mute some this feedback. I think it's Thomas. Just mute yourself. Okay. So for the inductive hypothesis, we assume that P of K is true for an arbitrary non-negative integer K. That is, we assume that 1 plus 2 plus 2 squared plus plus 2 to the power K will always equal to 2 to the power what? K plus 1 minus 1. So we have the inductive hypothesis. On the inductive hypothesis, that's where I said that you need to make an assumption that if it is true for the basis step, it must be also true for P of what? For P of K. So in other words, where we're having an n, we are going to put a K. So we are going to have 1 plus 2 plus 2 squared plus plus 2 to the power K is equal to 2K plus 1 minus 1, just like that. So to carry out the inductive step using this assumption, we must show that when we assume that P of K is true, then P of K plus 1 is also true. That is, we must show that. So in other words, whenever this one is true for P of K, it must be also true for P of K plus 1. So in other words, we are just also going to take this one and put what? And put K plus 1 for n. So what we are going to get, they are going to get 1 plus 2 plus 2 squared is just 1 plus 2 plus 2, 1 plus 2 plus 2 squared plus plus 2 to the power K. Why 2 to the power K? 2 to the power K plus 1 is just the next term after 2 to the power K. So we are just going to have this one, this whole thing. And then we add the one with the 2 to the power K plus 1. Like just what we're doing here. We started 2 to the power 0 and then 2 to the power 1, 2 to the power 2, just going up. So yes, 2 to the power K, then 2 to the power K plus 1, just like that. So what you are going to get is that 1 plus 2 plus 2 squared plus plus 2 to the power K plus 2 to the power K plus 1. This is what we get for P of K plus 1 must be equal to, then we put K plus 1 pana n up. What we get is 2K plus 1 plus 1 here, then minus this 1. So this is what we have. So when you have these two things, you now have to prove that this left-hand side can be the same as the right-hand side. So you can simplify the right-hand side as 2 to the power K plus 2 minus 1. So I want to show that this whole thing can be equal to this one. If you manage to show that, then you have managed to prove that by mathematical foundation, by mathematical induction, the given statement is what is true. So how do you do that? You need to make use of the inductive hypothesis. Ungaona ukaita induction wobva wasvike paanswer usina kushandise this P of K. Wozwa kuti wakanganisa handiti? You need to use the inductive hypothesis for you to prove that it is true for P of K plus 1. Because remember I say if it is true for P of K, it must be true for P of K plus 1. So you must always use the inductive hypothesis just like that. So what you want to do here, if you look at this part, this whole part, up to 2K, up to 2 to the power K, is just the same as this part. So which means we can take this right hand side and put it here. So that's what we are going to do. We are just going to take, we have got this part, which is equal to 2 to the power k plus 1 minus 1. So this is the part that we are going to replace. That's the part that we are going to replace this whole part. We are going to replace it with what? With 2 to the power k plus 1 minus 1, which is the inductive hypothesis. Then after using that inductive hypothesis, we need to simplify so that we end up having something like this. So how do you do that? I think it's now applying the laws of indices. I'm sure you know the laws of indices from your O level. Indices are these are just powers. So those laws you need to know them. So what you do here, you end up having 2 to the power k plus 1 minus 1 plus 2 to the power k plus 1. So it's as good as you end up having 2 to the power 2k plus 1 plus 2 to the power k plus 1, then minus 1. Whenever you are adding 2 to the power k plus 1 and 2 to the power k plus 1, it's as good as you are adding x and x, you get 2x. That's why you're getting 2.2 to the power k plus 1. Right? Then minus 1, because here we are not multiplying, we are just removing these brackets and add these two, because they are like terms. They are like terms, we can add them. Then whenever you are multiplying numbers with the same basis, therefore the same basis, you can always add powers. I'm sure you know that law in laws of indices. Whenever you are multiplying maybe numbers with the same base, you can add what? You can add the powers. So remember, this is 2 to the power 1, and then this is 2 to the power k plus 1. So what you do there, you add the powers. So it will be now k plus 1 plus 1, which will give you 2 to the power k plus 2, then minus 1. So if you look at this result and this one, you see we have the same thing. So in other words, you have managed to prove that by mathematical induction, then the given hypothesis is what? Or the given function is what? Is true. That's what you do then. That's what you do then. We have derived the left-hand side and make it equal to the right-hand side. So note that we use the inductive hypothesis in the second equation in this string of equalities to replace this part, like what I was explaining. We have completed the inductive step because we have completed the basic step and the inductive step. By mathematical induction, we know that P of n is true for all non-negative integers. That is, this statement or the given statement is true for all non-negative integers, n, just like that. So that's how you prove by mathematical induction. So you can be given many questions on such kind of proof by induction, but the method is just the same. The first thing is the basis step. Prove for those the numbers which are in the domain, right? And then you go on to the assumption. After giving an inductive hypothesis, which is the assumption, which is P of k, then you prove for P of k plus 1 using the inductive hypothesis that we have gave. Once if you manage to prove that the left-hand side is equal to the right-hand side, you can now claim that by mathematical induction, you have managed to prove that the given polynomial or the given P of n is what? Is true. I don't know if I have some questions on this one. Don't know if I have some questions on this one. Do I have hands on? No, I do not. Any contribution? Okay. Let me move on to proving by divisibility. Proving divisibility results. So we are still using mathematical induction, but now you are being asked to prove divisibility results. So mathematical induction can be used to prove divisibility results about integers. For example, use mathematical induction to prove that n cubed minus n is divisible by 3 whenever n is positive integer. Solution to construct the proof is that we will let n denote the proposition that n cubed minus n is divisible by 3. So in other words, we are saying whenever you have an integer, if you take the cube of that integer, and you subtract that integer, the result that you are going to get is always divisible by 3. That's the claim. So we need to prove that by using the mathematical induction. So the basis step is just the same. We are just going to follow the same steps. We're going to have the basis step, the inductive step. We do the hypothesis, the inductive hypothesis, and then we go on to the inductive step. Once you have done those 3 steps, you can actually prove that the left-hand side is equal to the right-hand side. Once you arrive at that, you give a conclusion that the given statement is true, as it is proved by what? By the mathematical induction. So on the basis step, the statement that P of 1 is true because the statement P of 1 is true because 1 cubed minus 1 is 0, which is divisible by what? By 3. We've taken P of 1. Why? Because we are saying n cubed minus n is divisible by 3 whenever n is a positive integer. So we are taking positive integers. So 1 is a positive integer. You can put any other positive integer and you can test. So look at the domain, please, when you're doing the basis step. Otherwise, it's false because when I'm trying the basis step, it's not giving me the correct answer. Look at the domain that we are using. We are saying n is a positive integer. Maybe you can try to put the negative numbers there and then you get the wrong answer or the wrong result and then you claim it is not true. So make sure that you look at that one. Then after that, we've got the basis step. You prove that if you put 1 here, you're going to have a number which is divisible by 3. Therefore, the given statement is true for n is equal to 1. Then let's go on to the assumption. Suppose that the statement is true for n is equals to k. That is k cubed minus k is divisible by 3. So we can write that k cubed minus k is equals to 3 dot q. Remember that divisibility, when we say d divides what? N, you are going to have something like d dot something. I'm sure if you remember this one. So whenever we have something which can be divisible by 3, it means we can have something of form 3q, where we can say if we divide both sides by 3, we are just going to get a q this side, which means everything here is going to give us this exact integer. We assume that this one is going to be an integer. So in other words, k cubed minus k, if we divide it by 3, is going to give us q, which is the integer for some integer q. So this is our assumption. That's the assumption that you made if you are doing the divisibility. If you are trying to prove the divisibility results. So we need to prove that k plus 1 cubed minus k plus 1 is also divisible by what? By 3. Remember, we have actually given an assumption and you mark it equation 1. And the assumption was that if it is true for what? For p of k. That's why you've put a k for n. We're having here n cubed minus n. So it is going to be k cubed minus k, just like that. So for k plus 1, you're going to put a k plus 1 on n, which is going to be k plus 1 cubed minus k plus 1. And you can also claim that it is divisible by what? By 3. And then we prove that, right? And then you prove that. So you're saying this one must be also true that k plus 1 cubed minus k plus 1 is divisible by what? by 3. So how do you prove that? How do you prove that? Now that we have this side which says k plus 1 cubed minus k plus 1 is divisible by 3. You need to prove that this one is divisible by 3. So how do you do that? Let's expand this one. If you expand this one, you get k cubed plus 3k squared plus 3k plus 1. And then after that, you add this one, this part. That's we've got minus k plus 1. After that, what are we going to get there? We've got k cubed plus 3k squared plus 2k. Where is it coming from? This minus, if we multiply it, if we put it inside, we are going to have minus k. So this 3k minus k, we are going to get a 2k. And then this plus 1 minus 1, you're going to get a 0. That's why you are ending up having k cubed plus 3k squared plus 2k. Then k cubed minus k plus 3k squared plus 2k plus k. Where is this statement coming from? We are adding a k and subtracting a k at the same time. So we are doing nothing to this statement. It's as good as say minus k plus k is equal to 0. So maybe, how can I explain this? I think that's the direct explanation. We are just subtracting a k here. So it's k cubed minus k. At the same time, we are adding a k on the same side. So it's just as good as say we are just adding and subtracting a k at the same time. So we are adding nothing and we are subtracting nothing, just like that. So k cubed minus k plus 3k squared plus 2k plus k, something like this. After doing that, you can actually add these two things and you end up having 3k squared plus 3k. After doing that, you can factor out, before factor out, you can substitute this one. Remember, we have added this k, we have subtracted a k here, so that we can end up having something of this form. K cubed minus k. Remember, you must always use the assumption, the inductive hypothesis. So we're trying to find a way of using this. So end up having k cubed minus k is equals 3 times q. So we are going to replace this one by 3 dot q. After having that, you can factor out 3 here and you end up having the k squared plus k. So if you factor out 3 from all this, you're going to have q plus k squared plus 1. Then if you look at this one is something of 3r, which means it can be divisible by 3, right? So if you managed to show that when I put n as k plus 1, the result can be divisible by 3, hence the given statement is divisible by 3. So hence by mathematical induction, n cubed minus n is divisible by 3 whenever n is positive integer. So I think you need to take note of that when you are proving divisibility results. You make use of the assumption. You make use of the assumption. But the way you make of the use of the assumption, you take the right hand side and prove it that it can be divisible by that number. Whereas when you are just doing the proof by mathematical induction, the general one, you have to substitute the hypothesis, the inductive hypothesis, into p of k plus 1, just like that. So here you just to take the right hand side and then you prove. But along the proof, you must use the inductive hypothesis. And remember, on the inductive hypothesis on divisibility, you need to create an equation when you make the assumption so that you can substitute the left-hand side with the right-hand side on the expression that you be having or that you want to prove. So I don't know if I have got some question, excuse me, or some contributions on proof divisibility. So in other words, you mean you are okay with the proof by divisibility. So I'm not going to dive into trees. We are going to do trees on our next lecture, and then we do the graphs. We're going to do the graph theory. We will cover what we think we need to cover there. Cover what I think we need to cover there. And on mathematical induction, please do the questions of the form which are in this slide. Divisibility and the other one. And what else? I think that's what I want to add there, because I know there are a lot of things there. Do not want you to mutsvage makudo nekwasingawanikwa ndizvo. Okay, so overall, do we have contributions or questions? Because for today I am done. Okay, so if I do not have questions or contributions, I can call it a day. Thank you for participating.
Thank you.
Okay, you're welcome. So thank you, team. Just have a good night. I'm out.
Okay.